Hello everyone. In our earlier video, we discussed what is similarity in triangles, and we also saw that if we had two triangles in which the corresponding angles were equal, we propose that the corresponding sides also would be in proportion. That is, considering these two triangles ABC and DEF, since angle A is equal to, we constructed the triangles in such a way that the corresponding angles were equal. Angle A equal to angle D, angle B equal to angle E, and angle C equal to angle F. And we proposed that the corresponding sides were also in proportion. If the corresponding angles were equal, the corresponding sides also would be in proportion. But in this video, we are going to formally prove this proposal. AB by DE, this side corresponds to DE, BC corresponds to EF, and AC corresponds to DF. But here in this video, we are going to attempt to prove this formally. And in our earlier video, we also tried to superimpose one triangle on the other. Because they were of equal angles, we tried to shift them like this. And in that process, we found that these two lines, the bases of both the triangles were parallel to one another, right? So now we are going to use whatever we did in our earlier triangle. I'm just changing the naming of the triangle for our convenience. Let us consider this as a single triangle now, ABC, and let us consider this as a line parallel to BC, DE parallel to BC. Let us try to prove that this parallel line, which intersects the two triangles on either sides, are divide the sides of the triangle in some proportion. AD by DB equal to AE by EC. Let us try to prove this first. Of course, once we prove this, we can prove the other one just by adding +1 to both the sides of the equations, which we will see later on. That is not very important now. Now what we are going to try to do is try to prove this, considering ABC as a single triangle and DE a parallel line. Now first we have AD by DB. Where is AD? This is AD and this is DB. So in order to bring in this ratio AD by DB, let us consider the triangle ADE, and we need another triangle with DB as the base. So let me make a triangle here by joining BE. So I have a triangle DBE, right? So let us find the ratio of their areas. Area of triangle ADE divided by area of triangle DEB or BDE. The purpose is to bring in these two ratios, AD by DB, but we are comparing the areas of triangle ADE and BDE, the bases of which are AD and DB respectively. So let me write the formula for the area. Half into base, which is AD, into height, is the area of triangle ADE. And what about the triangle in the denominator? That is also half into the base of that triangle is BD into its height. Now we'll have to see what is the height of both these triangles. What would be the height of ADE? It would be a perpendicular dropped from E to its base AD. And what about the second triangle? Once again, a perpendicular drop from E to the base of that triangle. So it would be something like this, right? Dropping a perpendicular from E. I'm just putting dotted lines. It's not a proper construction, but Let's say that this is 90 degrees. Okay. So this is the height of both the triangles. The triangle DEB being kind of an obtuse triangle, the height is outside the triangle, right? So here the heights are the same. The heights of both the triangles are the same. So we can conveniently cancel the heights and cancel half and half both in the numerator and the denominator. So we are left with AD by BD. So the ratio of the areas of these two triangles is equal to the ratio of their bases, and which is what we wanted. Now we'll have to look at the left hand side, AEC, the side AC of this triangle, and we need the ratio AE by EC. So we'll have to consider the two triangles whose bases are AE and EC. So for that purpose, I'll have to construct a join D and C and make a triangle DEC, right? Now let me compare the areas of these two triangles. So in the numerator we have the same triangle, area of triangle ADE, and the denominator now we have the different triangle which is DEC, area of triangle DEC. The purpose is to bring in AE and EC as the basis. We need AE as a base and EC as a base. That is why we have taken the ratio of these two triangles. So by now writing the formula for area, half into base. Now the base is AE into height, and denominator would be area of DEC. Now the base is here EC. Half into EC into height. So once again, let's look at the height of both these triangles. The height of AED and the height of DEC, right, is a perpendicular dropped from D to the base AE or EC. So the perpendicular would look like this. Let me change the color. Yeah, this is the perpendicular. And once again we see that the height is the same for both the triangles. The perpendicular drop from D to AC would be the height of both the triangles. So once again we can conveniently cancel the heights, and also cancelling the halves on both the numerator and the denominator, we get AE by EC. So now we have something on the right hand side where the numerators are the same. It's triangle ADE on both sides. The numerator is the same. But what about the denominator? The first denominator has this triangle BDE, and the second denominator has the other triangle DEC, this one, right? And what we observe is the bases of both the triangles are DE, the common base. They have a common base DE. And what else is common about them? Of course, the height is common. Why? Because DE is parallel to BC. Since DE is parallel to BC and both the triangles lie within these two parallel lines, they are perfectly fitting in between these two parallel lines which are equidistant to one another. Parallel lines are always, they are at an equal distance from one another. So the height is also the same, the base is also the same. What more do we need? The area is also the same. So we can say that triangle BDE's area is equal to triangle DEC. The area, we are talking about area of both the triangles, both of them are equal. So these two denominators also are equal to one another. So now we have proved that the right hand sides of the equation 1 and equation 2 are equal, because this triangle's area is equal to this triangle in the denominator's area. So since the right hand sides are equal, the left hand sides can be equated to one another, isn't it? So AD by BD is equal to AE by EC. And this is what we were aiming to prove, right? Of course, we haven't proved what we had proposed in our earlier video. The corresponding sides are in proportion of two triangles which have equal angles, equal corresponding angles. But we have proved a part of it, because if you just add 1 to both sides, which I will show you in my next video, you will understand very clearly after looking at that video. Now let's not bother about this, but this is one of the results which has been obtained as a byproduct, because mathematicians have thought in this way. Looking at two triangles which had equal angles, they tried superimposing one on the other and found that two of the sides were parallel, and then they arrived at this ratio. But nowadays, all this process is not shown in your textbooks. Instead, what you have in your textbooks is this. And what is this? Let me read it out to you. Maybe something will strike you. If a line is drawn parallel to one side of a triangle, so let me draw a triangle. So it says a line is drawn parallel to one side of a triangle. So let me draw a line here. To intersect the other two sides in distinct points. Of course, it intersects in distinct points. So this is A, B, C, and the line intersects AB at D, and the line intersects AC at E. Then the other two sides are divided in the same ratio. So it says AD by DB is equal to AE by EC, which this is what we proved in our this page, isn't it? AD by DB is equal to AE by EC, and this in your textbooks is quoted as the most famous Basic Proportionality Theorem. This is the Basic Proportionality Theorem. And this being found by a mathematician called Thales. This is also known as the Thales Theorem, but we have arrived at the theorem in almost a similar way in which Thales himself would have arrived at this theorem, isn't it? But what we do in our books nowadays is the theorem is proposed to us in the beginning, and then we try to prove it, and in the process we by heart it. We by heart the theorem, its proof and everything. But the purpose of our channel is not by hearting. It is to understand the basics and to think in the way the mathematicians used to think in those days. So I hope you understood what we were attempting to do, and I hope in the process you have also understood how to prove your basic proportionality theorem, which is very important for y'all in your syllabus. Thank you.